Yep, thanks, Kasam. Good morning, everyone. I believe it's morning time in India, and thanks for joining our session today. So answering your question, Tushar, yes, it's going to be 4 sessions, 2 of them in May and the other 2 in June. We are planning to do it in a 2-weekly basis to just give everybody a chance to absorb these sessions and take their time understanding it. So I'm going to put my YouTube channel in the chat if anyone is interested to subscribe and see my other videos. And the main purpose of today's session is going to be around these 4 patterns. Primarily around, most of them are queue or messaging patterns, priority queue, pops-up pattern, queue-based load leveling pattern, and throttling pattern. So starting with a priority queue pattern, this pattern is primarily comes under messaging category and performance efficiency category of patterns. And this is one of the common things you will see in our patterns today coming under messaging category. And it's very obvious when we are talking about message queues. And in a way or another, it's going to contribute to enhance the performance of our application when we are using a message queue. And the main thing of the priority queue pattern is to prioritize requests that are going to be sent between different applications. So we are going to assign a high priority message or event to be processed or handled by the consumers sooner before other requests that has been already sent before. And the related patterns to the priority queue pattern are competing consumer pattern and throttling pattern. We are going to cover throttling pattern in our sessions today. So let's dive into the example to help us understand this better. So let's assume that we have an application and we have a consumer. And we have an Azure Service Bus, for example, the middleware we are going to use to facilitate the communication between the application or producer and the consumer. So from the application side, it's going to publish the events or send the messages to the message queue. And then from the consumer side, it's going to pull messages from the message queue. So far, so good. Now, what if we have a high priority message that we need to be processed straight away? Generally speaking, in message queues, messages are going to be processed in FIFO order, first in, first out. That's especially if you are using like FIFO queue in AWS or similar queues in Azure. But what if we have a high priority message that we need to be processed straight away? Normally, it will be placed at the end of the queue, waiting for its time to come when the consumer is available to process it. And if we want to give a high priority flag to this message to be placed at the top of the queue, this is what this pattern is about. So primarily, when we get a high priority message, what we are going to do is to place these messages at the top of the queue. So the consumer will get to process these messages first. And then we are going to follow with the medium priority messages and then low priority messages. So when we have another high priority messages comes in, it's going to be placed at the top of the queue so the consumer will get to process them faster and before any other messages in the queue that are maybe in a. If we get a high priority message, for example, it's going to be processed. Generally speaking, messages are placed in the message queue in a FIFO order, first in, first out. So when we get a high priority message, it's going to be placed at the end of the queue, waiting for its time or for the consumer to be ready to process it. But what if we want this message to be processed straight away? And this is exactly what this pattern is about. What we are going to do is to assign a priority for these messages. So it's going to be placed at the top of the queue so the consumer can process these messages straight away. And then it's going to follow the medium priority messages and then the low priority messages. So when we have another high priority message comes in, it's going to be placed at the top of the queue, so the consumer is going to process it before other lower priority messages that are already in the queue. And this is the core concept of this pattern. Priority queue option or feature is already provided in Azure Service Bus and many message queue systems. But what if your message queue provider is not supporting the priority queue? Or what if your system architecture already are using multiple queues in order to make the processing faster? In this case, we are going to have a different perspective or different view of things, where we are going to assign or create different queues in our system. And we are going to have high priority queue, medium priority queue, and low priority queue. And then our application is going to send the high priority messages to the high priority queue, and the medium priority messages to the medium priority queue, and the low priority messages to the low priority queue. And then from the other side, we can have one or more consumers that are listening to the high priority queue and ready to process messages in this queue. And then we can have a less number of consumers for the medium priority queue, and maybe we can have one consumer for the low priority queue. And I'm here, some of you already are saying, we are ending up having too many consumers to process all of these messages. At least we will have to have one consumer for every message queue that we have. And that absolutely makes sense. And it might make the cost a little bit higher for your solution. And one thing you can do in this case is to put all of these consumers in a pool. And instead of each consumer or group of consumers listen to a particular message queue, you are going to make all of the consumers listening to all message queues at the same time. But with a condition that we are not going to process any messages from a low priority queue unless we fully processed all messages in the medium priority queue and in the higher priority queue. So as long as there are messages in the high priority queue, no messages are going to be processed from medium priority or low priority. And this might be fine in some situations. And if this is the case, then we can have only one instance of our consumers, since all of them are the same, listening or pulling messages from different consumers or different message queues. And then we can scale them up and down based on our requirements and based on the number of messages that are stuck in the queue. Now let's talk about some considerations you need to be aware of when you use this pattern. First of all, the priorities. You need to define from the get-go how many priorities you need to define in your solution. Are they 3 priorities, medium, low, high, or are they more than that? And it has to be well communicated with the business stakeholders because it's going to affect how workflows are going to be processed or how certain business scenario is going to be applied based on the priority of your queue. Also, you need to design if you are planning to be able to process all messages at the same time, or you are happy to pause the processing on lower priority queues if you have overwhelming number of requests on a high priority queue. If you're required to process all of the queues at the same time, then you have to get back to the previous implementation that you have to assign a dedicated consumer to each message queue to be able to process all queues at the same time, and without having a too many number of messages in a high priority queue will affect the processing of other low or medium priority queues. Also, in a multiple queue approach, we need to check and make sure that high priority messages are processed and completed before we get into the lower priority queue, as we said before. Monitoring is going to be very, very important in this pattern. You need to monitor number of messages in the queue, and based on that, you are going to scale up or down the number of consumers that are listening to this queue. And also, you need to be aware of the additional cost that might be linked to this. The more consumers you will deploy, the more cost you will have to pay. Also, the scalability is very linked to monitoring, actually. Based on the number of the messages that are stuck in the queue, we are going to make our system flexible to be able to scale up or down based on these number of messages. And the best use for this pattern is when you have your system is going to send or handle multiple tasks with different priorities. Either you're going to implement them in one queue or split them in multiple queues, but this is the core use case for this pattern. When you have a different priorities, you need to handle. One use case I would think of probably Amazon.com or any retail website. Usually in the retail websites, if they have a $1 million order, they put it in a different category and a different priority than $100 order. And this is kind of thinking that we need to be aware of when we apply priorities in our system. It won't work well for all industries. For example, in financial industries or investment banking, when you are going to send stock orders or stock market orders, orders has to be sent in the same order has been received from the customers. So yes, this pattern can work well in some situations or some industries, but won't work well with others. Also, it works well when you have different users or tenants, especially if you are a SaaS provider and you want to assign different priorities for different users or different tenants. So that's pretty much the first pattern, priority queue pattern. Jumping straight to the second pattern for today, publisher subscriber pattern, or some people prefer to call it pop sub pattern. And it's an old known system or software design pattern, and primarily comes under messaging category of cloud design patterns. And in this pattern, we allow the publisher or producer to communicate with one or more subscriber asynchronously. And also will allow the subscriber numbers to increase without affecting the infrastructure or affecting the publisher system or code. Now, coming to this example and see, we are going to have a publisher and we have one subscriber, and we are going to communicate between them asynchronously using a message queue. So the publisher is going to publish messages to the message queue, and the subscriber from the other side is going to pull or listen to the messages from the message queue. Then one more subscriber has decided to join our system, and in this case, we will have to build a new message queue that's dedicated for this subscriber, and we are going to change our publisher code to send a message to the yellow queue in order to be processed by the yellow subscriber. And this scenario is going to go on and on for every new subscriber who is willing to interact or receive messages from our system. And what actually is happening in here is that in every new subscriber coming in, we are creating a new message queue in order to put messages for this subscriber. And from the other side, we're making some application code changes at the publisher side to allow them to send the messages or events to the new message queue that we have created. So as you can see, it might work well for a small number of subscribers, but if you are planning to have millions or thousands of subscribers, that won't be possible. And this pattern exactly resolves this challenge. So instead of have one queue dedicated for every subscriber, what we are going to have is to have just one queue. So the publisher is going to send the message to one queue, and then this queue is going to broadcast the messages or events to all subscribers. This is not possible because we all know that message queue has been designed to send the message to a single consumer, and this is absolutely correct. And before we go forward, let's review a little bit the different queues available in Azure. We have Azure Storage Queue and Azure Service Bus Queue, and both of these are being designed to deliver a message to a single subscriber or a single consumer. But from the other side, we have something called Azure Service Bus Topic, and as you can tell from the icon, it's designed to deliver a single message to multiple consumers. And this is exactly what we are going to use. So instead of creating one queue for every subscriber who is willing to interact or receive events from our system, we are going to have one Azure Service Bus topic and make it to broadcast all of the events or messages to all subscribers that are subscribed to our topic. By doing this, we will not have to do an application code changes at the publisher side for every new subscriber that's coming in to join our system, and we don't have to deploy additional infrastructure for every new subscriber as well. Coming to the considerations of this pattern, you need to use the existing technologies. You don't have to implement it from scratch. Azure Service Bus Topics, Event Hub, Event Grid are doing the same functionality out of the box. You don't have to invent this or do it yourself. Also, you need to think of a way how you are going to handle the subscription from different consumers. Is it going to be seamless subscription where they can subscribe by themselves, or you are going to have kind of a workflow or approval process to approve a certain subscriber before they are subscribed to your events or your messages? Also, you need to think of the security to make sure that only subscribed users are allowed to receive your messages. And in some scenarios, some subscribers are interested in subset of messages, and you need to consider implementing some content filtering. If some subscriber is interested in a certain topic or a certain category, you need to allow them to apply this and do this to your topic. And also, wildcard subscriber is an interesting point. Some subscribers are interested to get everything you are publishing. And by using a wildcard subscriber, you are allowing them to receive every message you are publishing. Bidirectional communications is not supported in this pattern. And if you are planning to get something like to get an acknowledgement message from the subscriber, you need to consider implementing other patterns. Message ordering is not 100% guaranteed in the cloud message queues in general. However, they are trying to make it as much as possible to be FIFO, first in, first out, but it's not 100% guaranteed. So try to make every message to be like idempotent, isolated from each other messages, not dependent on a previous or a post message. In some situations, you might need to implement a prioritization for your messages, and you can use the message queue or priority queue pattern that we have talked about at the beginning as well. Also, you need to consider having a poison messages that has fault or has some kind of errors. And Azure Service Bus Queue has already, and topics as well, has inbuilt poison queue. This is where the poison messages are going to be directed to the poison queue after a certain number of retries, maybe 3, 5, 10. It's configurable number. You can choose it yourself. Also, message in cloud message queues, the message is guaranteed to be delivered at least once. So there is a little bit of a chance that your message can get delivered more than once. And you need to design your system based on that to make sure that if your message has been delivered more than once to the subscriber or to the consumer, it won't make any harm. The default message expiration in Azure Service Bus Queues is 14 days. However, you might not need that long expiration time for your messages, and you need to pick up the expiration time that works for your system or your solution. Also, create a message and put it in a message queue, but it will be only available for consumers at a certain time in future. So using this pattern when you want to broadcast information to multiple consumers at the same time without the need to deploy multiple infrastructure or making application code changes every time a new consumer comes in. Also, it's been used when the subscriber doesn't require a real-time response from consumer. Like you send them forget messages, it's not waiting a real-time response to come in back. So that's the second pattern we have talked about for today. Moving to the queue-based load leveling pattern. And it's one of the interesting patterns, actually. This pattern comes under many categories of cloud design patterns. First and foremost, messaging, very obvious because it's message queues. And then it contributes to the resiliency, reliability of the system as well. And we are going to see this in more details in the example. So this pattern is primarily trying to use a queue as a buffer between the task and the destination, between a service and a database, or probably could be anything. Related patterns to this pattern, competing consumers and throttling pattern. Now let's think of a scenario where we have a group of users are using our service. Our service could be API or web app service, anything you could think of. And then the users are going to interact with our service. And then on the background, the service has to interact with the SQL database to perform different sorts of operations. So far, our architecture is good. Our service and database are able to handle the number of requests we're receiving based on the small number of users that are interacting with our system. But when our service becomes more and more popular and more users are interacting with our services started to get more requests than usual. And in a way or another, it's going to affect our service limited capacity. When it comes to CPU or memory utilization, it has a limit. And when the number of requests has exceeded the normal limit, the SQL will start to deadlock certain exceptions or deadlock certain requests or ignore certain operations in order to allow the SQL to perform other operations that it's busy with. And we might think of a small or two quick wins we can do straight away on the SQL side that might solve the problem, okay? We could think of auto-scaling, for example, by increasing the tier of our SQL instance. By assigning more computing power or more memory for our SQL instance, it should allow the SQL to be more ready to handle the increased number of requests. This is definitely one approach we can do. Also, what we can do, we can have one or more read replicas. And the main purpose of this is to offload the read load from the primary database to these read replicas to allow the primary database to focus on the intensive or extensive write operations. So these two approaches could be really easy and quick to be done at the SQL side. So let's assume that we have gone and scaling the SQL database to the highest tier, but we're still getting too many deadlocks. And we are getting too many requests from our users that the SQL engine cannot handle. And in a way or another, the SQL is going to kill some requests coming from our service, and it's going to be propagated to the end user, telling that our service is not available or starting giving them errors. And this is what are we trying to avoid in here. So let's clean this up and think what we can do and how can we implement a queue-based load leveling pattern. So instead of our service directly communicate with the SQL database, what we are going to do is to introduce a message queue in between. So our service is going to send the different requests to the message queue, and then the message queue is going to trigger an Azure Functions app for every message placed in the queue, and then the Functions app is going to make the right request or right operation on the SQL database. So when we get an overwhelming number of requests from the users, the service job is just to break it down and put these requests in a message queue. And then we can get back to the user and tell them, okay, your request has been fulfilled in a way or another. Assuming, of course, that we have done a proper validation. Service has to be done before we place the messaging. And it's in system capability to process these requests we are placing in the message queue. So this works in some scenarios, not others. So again, coming back to Amazon or any e-commerce website, when you place an online order, you get a confirmation straight away that your order has been placed successfully. But maybe a few minutes later, you get another email telling you that, okay, this item is not available anymore in the warehouse, or maybe your credit card has been expired. And what this tells you that they're processing these back-end checks in a queue-based format. So when you send your order to Amazon or any e-commerce website, they're telling you, yes, your order is accepted. And then they are do their validations at the background. And if something is wrong happen, they are going to notify you again. Again, it's based on the industry, based on the scenario. At the end of the day, if you placed an order and your credit card is expired, it's not the end of the world. They can get back to you and tell you, okay, do you want to update your credit card or put a valid credit card or something like that? However, in another industries, it won't be possible, or it won't be as easy as that. Taking a financial or a banking system example, assuming that we are trying to do a cash withdrawal operation with $100, and the request has been sent to our service, and the client balance in the database is $100. If our service is going to do the cash validation, it's going to say, yep, everything is perfect. The client has enough balance, enough cash in their balance, and they can perform the operation. And then the service is going to place this request in a message queue in order to be processed. For some reason, this request is still stuck in the queue. Maybe the database is busy doing other stuff, but this request hasn't affected the balance in the database yet. And then the same user has put forward another cash withdrawal request with $50. And if our service is going to check the balance with the database only, it's going to seem like, yep, you can go ahead and withdraw $50 more. And if it neglects that there is another cash withdrawal request stuck in the queue with 100, probably our service will be unreliable and give false information to the customers. Yes, of course, the customers will be happy to withdraw $50 more, but our bank will be bankruptcy in really few months. And what our service needs to do in this case, when we are performing the cache validation against the database, is to consider, are there any more messages stuck in the queue waiting to be processed? And take this into the consideration. Maybe you are netting both balances and then coming back with a net balance and say, okay, this client has zero balance and cannot perform any cash withdrawal operations anymore. It may be like that. So when you implement this pattern or use it, be very aware of what business scenario you are using this pattern for. Some considerations we need to be aware of when we use this pattern. We already know that when we place messages in the message queue, it's going to trigger a separate execution of Azure function to execute these messages. But if you decided to put 1 million messages at one time in the message queue, which is going to trigger 1 million Azure functions to be executed, all of us know that SQL database won't be happy about that. So you need to consider how the capacity of the destination of your service. Is it able to handle 1 million requests or 1 million execution at the same time, or much less number? Of course, it will be much less number. So you need to be careful about that. The rate you are putting messages in the message queue, so the destination can still handle it. Again, the message queues are one-way communication. If you wanna get an acknowledgement message, you need to apply some other patterns like asynchronous request response pattern or something. Also, you need to be aware of competing consumer patterns. If you are going to apply an auto-scaling and have more than one instance of your Azure Functions app, and all of them are competing to try pull messages from the queue at the same time, you might get one message to be processed more than once, because probably it gets pulled by two Azure functions at the same time for processing. So you need to be aware of how you are going to look your messages in the message queue to be only processed by one Azure function. Again, using this pattern when you want to decouple or loose couple the dependency between different components of your services and prepare your service for heavy workloads. And you shouldn't use this pattern if you are expecting a really fast response from the end service, that you can't wait few seconds to get a response from the service. This is not the right pattern to be used. And actually, to be honest, it's not for read operations. I would assume it's more for write operations, because read operations could be redirected to read replica. It will be more efficient than using this pattern for a read operation. Now, moving on to the last pattern, the throttling pattern. And this pattern comes under reliability and performance efficiency categories of cloud design pattern. And the main purpose of this pattern is to control the rate the users can use or can call our service. And the main purpose of this is to avoid one single user to consume all bandwidth or all computing power for our service and make it unavailable for other users. And we're going to see this in more detail in the example. So related patterns, priority queue, queue-based load leveling pattern that we are talked about earlier. Now let's assume that we have a group of users that are interacting with our service. It could be API or Azure App Service or any other front-end service in Azure. Then the number of users has increased for a reason or another. And then all of these users are interacting or consuming our service. And so far, our service are able to handle these number of requests. Now we have got certain group of users decided to send more requests to our service. And it exceeds the number of expectations that we have planned our service to do. So what's going to happen that our service is going to be really busy to respond to these requests coming from this particular user. And it might affect our service ability to perform or execute requests coming from other users, because we haven't got a throttling limit yet. And all of the bandwidth or all of the computing power has been absorbed by this group of users. So our service won't be available to serve other users. And then other users might question themselves, are they using the right service, or they may need to switch to other vendor because our service are not able to provide them with the right service or right response. And then in a way or another, it might affect our service and make it unavailable. If we are under denial of service attack and someone decided to send too many requests to our service to make it unavailable for other users, that would be perfect situation for them to bring our service down. And you might think as a quick fix for a denial of service attack that we can scale up our service and make it to run on a higher computing power. And this would make sense a little bit, but the attacker from the other side is going to increase the number of requests they are sending to our service. And sooner or later, they are going to be able to penetrate through our service and make it offline or disable our service. So yes, if we are under denial of service attack and you auto-scale your service or you scale up our service, you might buy some time before the attacker will disable your service completely. So by implementing throttling will provide a lot of benefits, not only from reliability perspective, but I'd assume it's from security perspective as well. Although it's not said clearly in the Microsoft documentation that it linked to security, but I would count it as a security mechanism you can use to protect your service, especially if you are a SaaS provider with millions of customers. Now let's talk about some throttling strategies you can use. First of all, that you can start rejecting requests once they exceed a certain limit or a certain number of requests. And this screenshot here from API management, you can limit number of calls that you are receiving or usage quote per key. And it's as simple as you can define number of calls in a certain period of time based on a certain IP address or a subscription key. And once the user exceeds this limit, they are going to receive 429 response code, which is telling them that they are sending too many requests to the service. Can you mute your mic, guys? Someone just had his mic unmute. So, yep, perfect. Someone has his hands up. Yep, go ahead. Number 11, I'm not sure. Yep, you can go ahead. All right, cool. So when we exceed this number of requests, it's going to block the user, this particular user, and our service will still be available for other users and serve their requests. This is definitely one mechanism we can use, and it's already out of the box provided in API management and in Functions app. You can define throttling limit for your functions or your API management. Also, second strategy you can do is you can disable or degrade the functionality of your service. You could think of YouTube, for example, or any other video streaming application. When they get an overwhelming number of requests, instead of disable their platform altogether, they scale it down to run on a lower resolution and to be available to the end user, but it runs with a lower quality than usual. It saves the day at the end of the day if something bad happened to your platform, or you are getting too many requests that you cannot handle. Also, third strategy you can use, and we have already talked about it, is use queue-based load leveling pattern. So when a message comes in, you are going to place it in a queue and to be executed at a slower pace against the database, so it won't make harm to your overall solution. Also, what you can use is to implement a priority queue pattern. So when you have a high priority pattern, a high priority message, you place it at the top of your queue to be processed by your consumer sooner than other messages in the queue. This also could be one of the strategies you apply in the throttling. Like when you hit a certain throttling limit, you just will accept high priority messages and defer other lower priority messages until the rates become normal again. Also, the fourth and last strategy for throttling ones are deferring operations that are performed on a lower priority application. So when we hit the throttling limit, probably we can decide, and it's a business decision, what are the system features that are not quite important as others? Like what are the non-essential features that we can neglect for a certain period of time to allow other essential features to be up and running? And we are going to see this in this graph here. So assume that we have 3 features in our system, and this is the time. And we had hit the limit in here. And once we hit the throttling limit, we have decided to stop processing feature B because it's non-essential feature. And this is to allow feature C and feature A to continue processing until it gets back to the normal. Then we continue processing feature B again. It could be one of the strategies that we implement as part of the throttling strategies. Also, throttling and auto-scaling comes really handy when you use them together, because all of us know when you auto-scale your service, it won't be auto-scaled in a second. It takes some time to warm up and for the new infrastructure to be placed and ready to accept the traffic. Until this time happens, yes, it's a few minutes, but till this time happens, you want to make sure that your service or your platform won't be unavailable. because it's getting too many requests. And what's going to happen in here, if we hit the softest throttling limit, we are going to scale down the number of requests we are able to process. This is to save the platform from failure. This is also to give time for the auto-scaling services to take place and to be able to ready to receive requests. And once this happens, we will be able to return our throttling limit to the normal, and then we are going to have another throttling limit actually, because we have now scaled out or scaled up to more resources to be able to handle the increased number of requests. Now, talking about some considerations we need to consider when we use this pattern. That throttling is an architectural decision that needs to be incorporated into your system design from the get-go. Yes, you can apply it at any point of time, especially if you are using Azure Function or API management. It's really easy and plug and play. But if you are planning to customize your throttling limits, pretty much as we've seen in these graphs, where you are going to pause certain features or degrade certain features, it's an architectural thing that you need to consider and incorporate into your system architecture from early on. Also, when you apply throttling, you need to perform it quickly, because as we said, you might be under attack, denial of service attack, and you need to perform or respond to this action as soon as possible. Also, if you are not under attack and your service getting too many requests, you need your service or your auto-scaling to be effective as soon as possible to be able to process this high number of requests you are receiving from the external users. Also, sometimes when we get high number of requests, it's not denial of service attack all the time. Maybe the user, it's a genuine user sending too many requests and he has no idea that they might make many harm to our system. And if we just send them response code 429 or telling them that they are sending too many requests, probably they can stop sending these, increase the number of requests, and we wouldn't need to do any auto-scaling or anything else. So it's very, very important to respond with the right response code to tell the consumer of your service that they are doing something abnormal. And as we said, we can use the throttling as a mechanism to protect the platform until the auto-scaling or scaling up and down event take place. Again, when you use this pattern, when you have an SLA, you need to meet with your clients and consumers, and you want to make sure that not a particular client will be able to disable or take all the computing power of your service and make it unavailable for other users. And also, when you have a high number of requests being sent from a particular user or for a certain activity, you're using this pattern to limit or to make sure that high number of requests for a certain feature will not disable all features in your system. Also, it would allow you to perform kind of cost optimization, because you're not going to run to auto scale every single time you get an increased number of requests. You try to apply a throttling limit first and see if it's going to be fine with the client. And if not, then you can go to the next step and apply an auto scaling if you need to. Now we're coming to the end of this session. We have discussed the 4 patterns for today: priority queue, queue-based load leveling, pops up, and throttling pattern. The main common theme for these first 3 patterns is the messaging. They are primarily using message queue to facilitate the communication between producer and consumer, and the throttling pattern is effective with all of these 3 patterns and more actually. Actually, throttling pattern is one of the important patterns that you need to consider. And if you are in Azure, so native Azure services like Functions app or app service or API management, it's highly recommended that you specify a throttling limit for your services. Sometimes the business owners might not know what are the throttling limits that they need to define for your services, or they can't imagine how many requests that the service should be able to process per second. In this case, you try to aim high, maybe 100 requests per second or something, or maybe thousands, and then play with it up and down to hit the right throttling limit that reflects the reality. It will help you one day if you are under attack and someone trying to break into your service. It will be a very effective mechanism to stop this attack before happening. So yeah, that's it for this session. now we can talk about any questions. If anyone has any questions, please feel free to put in the chat window.
Hi, Hussein. I have one question.
Yeah.
Hello.
Sure.
Related to the Azure Service Bus queue. So I have set up a Azure Service Bus topic with the 2 subscriptions, one of a high priority, one for the low priority. And, I have a for a SQL filter on the subscriptions, and I verified that message are being correctly routed, but the priority is not being taken to both accounts. So is there any way to prioritize this service bus queue so that I can?
Yes, you can put a topic in the message, or put a category or a priority for each message if you are using one queue, or you can split them into separate queues altogether and have one queue for high priority messages and another queue for low priority messages, and then your producer or your application will be sending the message and put the message in the right queue based on that. Does this answer your question?
Yeah.
Hussein, we have one question from Manish.
Yep.
Like you please
yeah,
share.
I saw it. Okay. Yep. Someone said yeah. About using message queues like enterprise applications. It's in the list. Use cases could be used for the using the message queues. As we said already 2 scenarios for e-commerce or banking system. It could also useful for actually anything could be applied. You can apply the message queues in all situations. The most critical one is the financial. You just need to be very careful about it. But generally speaking, all industries should work well with these message queue pattern. And the main concept or mindset that you need to apply in here that nothing is happening in real time. Even if you are in synchronous operation, it's not real time. It takes some time from your service to go to the database to execute the request and come back with the result. Yes, it's a milliseconds, but it's not a real time. And what matters in here and what question we need to ask ourselves here, how much seconds are we comfortable to wait until a certain request or operation to be executed end to end? So yes, e-commerce example, what else? It wouldn't be a good idea to use this pattern, for example, for authentication. If you are sending a username and password and expecting to get a response straight away, whether you have provided the right credentials or not, doesn't make any sense to use this pattern because it's not gonna be useful. Maybe it will make the user experience a little bit worse. Maybe in file uploads, for example, instead of file uploading or if you are uploading a large number of files to a certain place or a file server, it will be more efficient. And actually, it's another design pattern. Hopefully, you are going to talk about it later. It's going to be more efficient if you put the file that you are trying to upload in a blob storage and then put the metadata in the message queue. So you are going to put the message headers or ID or IP or ID of the user or client, and then with a reference to the blob storage location. And then when the message passed to the Azure function, then the Azure function is going to pull the file from the blob storage instead of just putting the file itself in the in the message queue, because all of us know the message queue has a limited size. Like, I'm not sure what exactly, but the difference between the storage queue and service bus queue is the storage queue has 256K size of a message, while the service bus queue can have 1 meg file of a size of a file, so it won't be suitable to store or pass large file in these middleware. How do we could design patterns differ from general? Okay, so the cloud design patterns are like they're overlapping a little bit, especially like the PubSub pattern. It originally comes from software engineering pattern, but it has a cloud flavor into it. Like some of the patterns, probably you have talked about it in the previous talk. It was primarily about the gateway patterns, how you are going to protect your services using gateway or gatekeeper pattern. So you are going to have layers of security in front of your backend services in order to protect it. In addition to the gateway offloading, instead of applying or implementing authentication authorization yourselves, you can offload it to Azure Active Directory or B2C to just make the implementation easier for you and to make you depend on a more highly available service as well. So they are a little bit different, but it has a flavor, cloud flavor onto it. Poison message is a message that has a failure. Maybe it comes in an incorrect format or message that couldn't be processed for certain number of retries, like message kept failing over and over and over when the consumer tried to process it. We call this a poison message. So we want to stop the bleeding and stop the consumer from pulling this message and try to execute it over and over because it already tried to execute it 5 or 10 times or whatever, and for some reason it couldn't. So it has some wrong data, comes with the wrong format, or it's a wrong request. And what's happened in this case, we put this poison message in a poison queue, and it's already built-in feature in Azure Service Bus. And then we can see how we can process these poison messages in the message queue. If you are in a really big enterprise, you could consider a solution or a situation where you can handle these poison messages in the poison queue automatically. But if you are in a small scale and you are not expected to get large number of poison messages, you can handle them manually as well. I don't think there is a limit on the number of messages you can put in the queue, especially in the cloud. It might be relevant in all the on-prem servers, but in cloud, there is no limit for the number of messages you can place in the queue. But if you want to have a chain of queues, probably it's going to be efficient to try to break your business logic to priorities and have different queues set for different priorities or even different operations. Instead of having all operations being sent to one message queue, try to split your operations across 5 or even 10 queues. So you are able to process all of them in parallel instead of just waiting for one queue to be able to process all of these messages. First part of your question, yes, caching is a good mechanism to use. And sometimes, and it's a pattern you called content host pattern, if I remember it correctly. But what it does actually is to try to put your static web content in a blob storage and put it behind the CDN or content delivery network to allow it to be synchronized across the globe. So when people try to load the static data from your website, whether it's GSS or PDF or any other audio files, it will pull it from the blob storage behind the CDN. It's not going to affect or overload your web servers. And this is actually a good pattern to use to free your web server to handle the dynamic requests that are coming from your client. Does this answer your question?
Yeah, sure. Only thing is that priority queue would not work in our case because we want to process the messages in a particular sequence. So in that case, priority, there is no priority in our case. So I was just so that's why I was thinking that the messages can be in the same order as it was received, but maybe we can chain those queues. But I agree. Ours was on premises and not on cloud. So you might be right there that because we had a limit. And we were reaching that limit very soon because we were not able to consume those messages as fast as we were receiving it. Hence, the size was growing. Yeah.
What you can do is to have multiple consumers or scale out the services that are listening to the queue, so they can pull messages in a more quicker rate than the producer can produce them.
Unfortunately, that was also not working because, as I said, we have to process them as we receive it. So I cannot have multiple consumers doing it in a different way. Yeah. So it have to be in the same orderly manner. Yeah.
Okay, it's a good one. Let's continue the chat on LinkedIn. We can definitely chat about this in more details later. But thanks, it's a really good one.
Yeah. So you have a LinkedIn. You're going to share a LinkedIn.
Yes. Yes, I sent my. Okay, I'm gonna put my okay, that's my YouTube channel. I'm going to put my LinkedIn in a minute.
This is the